Again, my name is Ryan Kearns with Monte Carlo. I'm one of the founding data scientists here. And today I'll be talking to you about avoiding thin ice, scaling data reliability in Iceberg. I worked on scaling out the initial anomaly detection infrastructure, and now I do a lot of ML ops and unsupervised learning and run slide decks. There we go. Okay, I can advance. There we go. So just to give some preamble about Monte Carlo and about my position within the company, just to kind of the ethos for our place in the discussion here. So we are the leading data observability vendor that sells basically an end-to-end data observability solution that can integrate with various different data lakes, lakehouses, warehouses, business intelligence tools, really you name it. We've got a 30,000 user base, and when we say here we resolve 1,000 data incidents a day. I'm a data person, so it's probably around 1,000. We're working with 300 customers in production, and of course, rankings from G2 and other kind of industry leaders there. So I work here as a founding data scientist, as I said, and I've worked a lot on our anomaly detection infrastructure. And what I want to talk about today is this sort of brief history lesson, I guess, running through the different pipeline architectures and how these have evolved over time and the implications these have for data quality and data observability. And we can just sort of run through the examples and sort of see how we've evolved in this continuing pattern towards more decoupling, more customization and democratization of data access, and what that implicates for data quality if you're interested in having sort of a gold standard data quality product for internal or external users. So starting with the ELT domain, if we're talking about sort of Hadoop era on-premise compute, apparently people used to run databases on-premise, maybe before I was alive. And in that sort of ETL infrastructure and that dogma, you're running the transform in place before the load. Okay, so I can write some static unit tests. I understand the data sort of pre and post transform. I can maybe set some expectations around provenance or around certain relations that are expected to hold. So maybe actually get a lot of leverage around unit testing. And of course, there's a difficulty defining the invariance that you want to enforce in the system and how to ensure that you're actually measuring the correct things to ensure quality. But it seems relatively simplistic compared to what we'll call the modern data stack and the sort of ELT paradigm, the sort of DBT paradigm, where I'm running my load and then I'm running my transform. So now I'm working a bit faster. I'm automating more pipelines. Data is able to move faster between different storage formats and environments. And so I may not necessarily be able to write a unit test that can give me those same guarantees around provenance or around the integrity of a certain field, maybe if it's moving through an ingestion layer in between. Okay, so that's a little bit more complicated. Things are a bit faster. As a result, the reason that we actually move towards more flexible and performant data architectures in the first place is I'm running much more complicated BI. I'm running some machine learning applications now in this architecture. And those can be a bit more nuanced. And also the space of my available data practitioners is sort of opening up. Now I've got more analysts that are working with the same data that's coming from a pipeline team. I've got machine learning engineers or data scientists working with that same pipeline and having expectations around the schema and the availability of that data. So data quality is a little bit more important. And then we can move all the way to why we're here today, talking about the headless data warehouse, the lakehouse environment, and these decoupling systems like Iceberg that allow you to separate out the query engine from the storage format. And so now I really have a lot of extensibility. And as my sort of trend line here is attempting to show, a lot more potential vectors for data quality issues. Because I might have exactly the same storage format that's supporting use cases among, Spark jobs and Python notebooks, and I might be running various different OLAP query engines, low latency query engines. I might be running Snowflake alongside Spark, alongside Trino, and various other data providers. So it sort of sounds like the narrative is more data and more problems at this point. I think that the takeaway that I'm trying to give and the Monte Carlo method that we sort of apply to these types of data quality problems is that irrespective of those changes in architecture and all the innovations you've been hearing about earlier today, the standards for data quality really remain the same. And we take this really pillared approach to identify the 5 fundamental and unchanging attributes that guarantee high quality data. And those in order I'll start with freshness. This is just the implication, is my data arriving on time? Let's say I have a daily ELT job and I want to refresh a dashboard once per day to go into my executive meeting and display my new BI with the spend figures for the last day or the click-through rate for the last day. If that data is not arriving on time, and critically, if you can't be notified to the fact that that ETL job has stalled because we have an exploding join all of a sudden, or maybe we've lost permissions and the table is no longer refreshing, now we're in trouble. We have what we call data downtime, and we have this basically the equivalent of application downtime in our data-driven decision-making settings. Next, we have volume. You may start to notice with these pillars that they sort of define verticals for nice SLOs and SLAs, or how you want to guarantee high data quality. Volume is about the size of the data coming through. So I might actually have a table that's fine from a freshness standpoint, but if I'm expecting 10 million rows and all of a sudden I have 10,000, something's probably wrong with my integration layer upstream. Or if I have 100 million, something's probably wrong with the join that's happening in the query that's producing that data. And so volume can, if we're expecting certain trends to continue over time, or expecting rows added per partition to be roughly equivalent, we can start to identify data quality gaps there. Quality, I'm now stepping into the content of the data itself and no longer the metadata layer. So this is a bit more, I would say, non-trivial to introduce at scale. Obviously, you have to look at the content of the data itself, but maybe I analyze per partition, what am I actually receiving for my critical fields? And can I enumerate the various things that will be high priority to guarantee about that data? Are there no nulls? Do I have an 100% uniqueness rate for my field called UUID? Or do I have a string field that is always parsable as an integer, except in that one case it's not, and it causes an operational pipeline failure, right? So that's quality. Stepping back again to the metadata layer, we talk about schema, and all of these are interlinked with each other. So of course, Iceberg provides quite a lot of flexibility around real-time schema evolution. I did not mean to do that. And that can be extremely flexible, but we also want visibility into when that's changing, especially if we have different data personas that are expecting, one person querying a data from a Python notebook and another querying that data as part of their operational pipeline. If they have misaligned intentions about which fields are essential to have in that table, and one gets dropped for performance reasons, we can run into problems if teams aren't communicating properly. And then finally, lineage, tying this whole data ecosystem together. And I really mean end-to-end lineage. So the provenance of data, where has it come from and where is it going? So if I'm a pipeline engineer in the middle of the system, I might want to know about what is upstream, so what external tables are being loaded in for me to do my transforms. And are those coming from various different APIs? And is one of those APIs about to be deprecated? So am I dealing with, let's say I have a volume problem. Can I find the root cause of that using the table lineage? Or can I examine the implications of downtime using the downstream lineage to say, this table is critical to remain up. I need some SLAs around it because it feeds a business intelligence dashboard that gets reported directly to my executive team. So really, all 5 of these we say tie together and give us a guarantee of gold standard data quality. And critically, it's sort of invariant to the architecture that we're running. And I think that that's a kind of a meaningful takeaway. So it might sound like more data, more problems. I think it's really more formats, same fundamentals. And I can enumerate a couple of the things that we sort of see as key to guaranteeing high quality data. So first, like our metadata layer is going to be huge for leveraging out of the box freshness, volume, and schema monitoring. So if I go into my Iceberg metadata files and I'm looking for the last updated timestamp, and maybe I'm collecting that on an hourly cadence, now I have a time series that shows me how frequently this data is being changed, and I can start running anomaly detection. I can start finding the places where tables are routinely updating and then suddenly stop. Similarly with volume, I can pull the total rows added or the total rows contained in a partition or the rows added per partition update, and I can start maintaining expectations around those. I can actually scale that with machine learning if I just build a system that says, identify the tables with consistent patterns and tell me when they deviate. Likewise, I'll point out time axes. I actually think in the previous presentation, we talked about the magic of time axes, and they unlock a lot from a quality standpoint because they allow us to run partitions. and identify changes in the quality of data per partition. And then notifications, I think that's critical. Being able to tie all of this together into a framework to not just identify problems, but identify the relevant stakeholders in those problems and let them know, so that they can be able to triage problems in real time. You know, if you're firefighting a data pipeline at 8:45 a.m. before a 9 a.m. meeting, it's pretty important you get that time to detection down. And then also knowing where the gaps are, I think. Again, the sort of blessing and the curse of these more distributed compute and decoupled formats for storage and compute are that we can do a lot more, but we do it with identification of pain points, places where teams need to transfer domain knowledge, maybe have a data contract, and understand where your vulnerabilities are in the pipeline. And then as far as lineage, we're actually, this last point is slightly throwaway because we're now talking about the specifics of what query engine you're using. But you can really start to leverage query logs to identify lineage. This is sort of the key takeaway we've had at Monte Carlo, is that these are the key to understanding provenance and mapping sources to destinations in an automated fashion. I know that's a bit of a blitz through. I only have 10 minutes, but if you want to chat more, I'm leaving my email up there for any substantive follow-ups that you might want to give. And also, you can request a demo from Monte Carlo to see how we provide an implementation of these 5 pillars that I've just talked about.